In this video, we'll go over the building block structures and causal graphs that explain the statistical relationships that we observe in data. This will help us understand the patterns that lead to lack of exchangeability. There are three main structures in DAGs that serve as the building blocks for all graphical causal models. The first is called a chain. One variable causes another, which causes another. The second is called a fork. One variable is the common cause of two other variables. And the third is called a collider. Two variables both cause a third. The two arrows collide into a third variable. One variable is a common effect of two others. In all causal diagrams, these three structures make up the entirety of the graph. What patterns of independence and dependence, both marginal and conditional, are implied by these structures? Let's take a look. Let's start with chains. The fact that y is a function of x means that x and y are dependent. Because y depends on x for its value, there are going to be cases where changing the value of x will change the value of y. For the same reason, y and z are dependent. Combining these two conclusions, x and z are dependent. Because z depends on y for its value and y depends on x for its value, there are going to be instances where changing x will change y, which will change z. The last key property that is important for chains is that conditional on y, x and z become independent. Why is this? X and z are marginally dependent because changes in x do correspond to changes in z through changes in y. When we condition on y, we hold it fixed at some value. Within these subsets defined by y, values of x will still differ across cases, but these changes in x are no longer linked to changes in z because z changing depends on y changing. So a physical analogy that may help is to view this chain as a rope. Shaking the x end of the rope causes the z end to shake because the rippling goes through the middle of the rope, through y. But when we fix y, we essentially hold the middle of the rope still, and shaking the x end no longer transmits down to the z end. When we condition on a variable in a DAG, a common convention, which we'll use in this course, is to put a box around it. One small note, technically, the first three marginal dependence relations should be expressed as being likely dependent rather than definitively dependent. In most real-life situations, these variables will be dependent, but there are some very rare cases requiring exact probabilities that will still result in the variables being independent, despite these causal relationships. These situations are called intransitive cases, and some examples are discussed in the book Causal Inference in Statistics, a primer. But throughout our course, we generally won't deal with intransitive cases, so we'll say dependent instead of likely dependent. Let's look at an example. Having health insurance is a cause of healthcare utilization, which is a cause of lifespan. In particular, we'd expect that the relationships along the arrows are all positive relationships. Having health insurance increases healthcare utilization, and increased healthcare utilization increases lifespan. Thus, having health insurance tends to increase lifespan. But what if we condition on the level of healthcare utilization? Within a fixed level of healthcare utilization, there are still people with and without health insurance, but we would expect no differences in their lifespan. Why? Because by definition, they're using the same level of health services. If they use the same level of health services, they're experiencing the same level of health care and health supporting behavior. So we would expect no difference in average lifespan. Note that we're making the assumption that this causal graph tells a complete story of the world. Most importantly, that having health insurance only affects lifespan through the use of health services and not through some other means, like a greater willingness to exercise. If such a pathway were present, conditioning on healthcare utilization would not result in conditional independence because health insurance and lifespan would still be dependent through this exercise pathway. Let's summarize the properties of chains in more generality. No matter the length of the chain, any two variables on a chain will be marginally dependent. If x and y are two variables along a chain, they will be conditionally independent given any set of variables between x and y. So in the DAG shown here, x and y are conditionally independent if we condition on just b, just c, or both b and c. So note chains are important in causal context because chains from treatment to outcome represent causal mechanisms of interest to us. That is, chains generate causal effects. Now let's look at independence and dependence patterns in forks. In a fork structure like this, X is called a common cause of Y and Z. Because X is a cause of Y, X and Y are dependent, and because X is a cause of Z, X and Z are dependent. It's also true that Y and Z are dependent. This dependence is due to the common cause X. Changes in Y reflect changes in X, and those changes in X lead to changes in Z. So changes in Y and Z are linked. Lastly, even though Y and Z are marginally dependent, they are conditionally independent given X. The reasoning is very similar to the reasoning for chains. When we condition on X, we hold its value fixed, essentially filtering the data down to cases where X equals this fixed value. And then we look at the relationship between Y and Z in this filtered data. Y and Z were dependent because they were simultaneously responding to changes in X. But when we fix X, changes in Y and Z are just due to noise, so they are independent, conditional on X. Let's look at an example of a fork. Temperature is a common cause of both ice cream sales and forest fires. So temperature and ice cream sales are dependent, temperature and forest fires are dependent because both vary as temperature changes. When we condition on temperature, holding it fixed at a certain value, there's no longer any dependence between ice cream sales and forest fires. Let's look at one more example. Age is a common cause of shoe size and reading ability. Both shoe size and reading ability increase with age, and so shoe size and reading ability are also positively correlated. However, when we condition on age, we no longer see a relationship between shoe size and reading ability. So the common theme behind these examples is exactly the spirit behind the saying, correlation does not imply causation. The middle node of the fork gives rise to an association between ice cream sales and forest fires, between shoe size and reading ability, despite the lack of a chain, a causal mechanism, connecting them. Forks are a structure underlying confounding. For this reason, forks, where treatment and outcome are the end nodes, are a structure that generates lack of exchangeability. Let's summarize the unique property of a fork. If a variable x is a common cause of variables y and z, and there are no other paths between y and z, then y and z are conditionally independent given x. Conditioning on the middle node of a fork has the potential to let us achieve conditional exchangeability. The last structure is the collider. In this structure, z is called a collision node because two arrows collide into it. Because x and y are not causes of each other and don't have a common cause, they're independent. Both x and y are causes of z, so as we've reasoned before, x and z are dependent, and y and z are dependent. The last key property of colliders is that even though x and y are marginally independent, they become dependent conditional on z. Why is this? When we condition on z, we hold it fixed. Say it's some value little a. If we let x change, then y must change accordingly in order to keep z equal to little a. For example, say that x is the result of rolling one six-sided die and y is the result of rolling another, and z is the sum of the two rolls. X and y are independent, but once I condition on the sum, knowing the value of x absolutely helps me predict the value of y. I'll know it exactly. That is, once I condition on z, the sum, the two originally independent causes become dependent. Let's look at one more example of a collider. Musical talent and being the child of a veteran are marginally independent variables, and both contribute to winning a scholarship. The scholarship is awarded to students who either have strong musical talent or who are the child of a veteran, or both. There's a clear dependence between each and the scholarship variable. But what happens when we condition on the scholarship variable? In the scholarship winners, musical talent and being the child of a veteran become dependent. Using the intuition of the sum of dice example, when we fix the value of the scholarship variable, to yes and change musical talent, the value of the child of veteran variable must change accordingly to keep scholarship equal to yes. In particular, changing musical talent from yes to no requires child of veteran to be yes. Within the scholarship winners, this dependence arises between two variables that were marginally independent in the general population. Let's summarize the unique properties of a collider. If X and Y are causes of a common effect Z, and there are no other paths between X and Y, then X and Y are marginally independent. They become conditionally dependent if we condition on Z. And it's also true, using analogous reasoning as before, that conditioning on any descendants of Z will also make X and Y conditionally dependent. In the diag shown here, X and Y become dependent if we condition on any combination of the variables within the set Z, A, B. So, in short, conditioning on collision nodes can create lack of exchangeability. In summary, we've been discussing causal graphs as statistical models. In this video, we've highlighted key structures within causal graphs that give rise to statistical associations by discussing marginal and conditional dependence patterns. Understanding how associations in observed data arise is crucial for us because it turns out that these associations are a combination of causal associations, associations arising from causal mechanisms, and non-causal associations, misleading associations. In this video, we've seen how non-causal associations can arise through forks and through conditioning on a collision node. Moving forward, we're going to organize the independence and dependence patterns discussed here into a more general concept that can be applied to causal diagrams of any complexity. We'll use these ideas to formalize the notions of causal and non-causal associations so that we can ensure that non-causal ones are not present.